This is structural engineering channel. On this channel, structural engineering related courses will be delivered based on New Ethiopian Building Codes ESEN, which is Ethiopian standard based on European norms. Please subscribe, share and like our channel. For today we'll present example on slenderness of column as per Ethiopian standard ESEN 1992-2015. Question is, determine whether the column CD is slender or not. If it is subject to loads shown below, consider the frame to be non-sway using this material. Concrete strength 25 13 and the frame is given here. The question is to identify is column CD is slender or not. Cross section is given here, cross section of beam and the cross section of column, and the moment and axial forces from this axial force diagram and bending moment diagram. This is a moment at the end of column CD, at the top and at the bottom ends. So let's start our solution. Our solution will be based on Ethiopian standard ESEN part 1 of 1992 code. So start our solution step by step. The first step is to identify the slenderness of column, then compare with the limit of the column to classify as short or slender column. So in calculation of slenderness ratio, lambda, which is equal to effective length over radius of creation, where L is effective length and I is radius of creation, calculated by using this expression under square root moment of inertia over cross sectional area of concrete. So based on the code provision of lambda formula, let's see on the code. This is the expression on the code to calculate lambda slenderness of column is given on this part 5 or chapter 5 of our code in section 5.832. So by using this expression we will calculate our lambda. First calculate our effective length. Effective length is calculated by using this expression, beta times height of column. Height of column is a vertical distance between two floors, and L effective length is height between 2 points of contraflexure, which means the height between two zero moments along the column height. Beta is a factor depending on types of end restraint, is calculated by using this expression. In this expression, K is the flexibility of end restraints at the two ends, at the top of the column and at the bottom of the column, which is also given on our code. Picture provided by code. We may use effective lengths depend on the support conditions. From this expression maybe we use, but for general support condition or for any elements connected at the end of column, we may use this expression to calculate effective length. This is for braced member, this is for unbraced member. So in this calculation, K1 and K2 only calculated by considering only members properly framed into the end of the column in the appropriate plane of bending should be considered. So before proceed our calculation, let's first calculate parameters on this K expression. Moment of inertia of our column based on given cross section of our column from the given frame, and the moment of inertia of our beam connected to that point from given from frame diagram. So substitute these values on K expression. E is common because our element is concrete, the same for beam and column. Modulus of elasticity is the same. So K1 is 0.1532. Then K2 for fixed restraint K is 0, but in reality we cannot provide full fixity, so at least we use so it is fixed. Let's use 0.1. At end 1 or at point C we say K1 calculated based on the connected elements, two beams and one column. So that is why we say here two times relative stiffness of beam, which is to represent the two beams. So let's proceed our steps. So E is beta times lambda. Substitute the values of beta and length given on the diagram. Length of our column is 8 meters. Substitute the values. L effective is equal to this beta times height of our column, which results 4,870.42 millimeter of effective length. Let's calculate radius of creation. Radius of creation is under square root moment of inertia of column over cross-sectional area of column. Then substitute the values which were already calculated in the previous slide. Our radius of creation is 150.47. Now substitute this effective length and the radius of creation in lambda expression. We get 42.12 slenderness values for our column. Next step is calculate. On the second step, calculate the slenderness limit. Slenderness limit is provided by this formula for isolated member. On our code, lambda limit is calculated by using this formula. On this formula, A is calculated by using effective creep. B is calculated based on mechanical reinforcement ratio. C is calculated based on end moments of a given column, and this depend on axial force. In case if our value of effective creep, mechanical reinforcement ratio, or end moments are recommended to use these values in case if they are not provided. But for our case, we have end moments. We can calculate our C value. C values depend on end moments, first order moments M01, M02, always, which is M02 is positive and the greater one, first order moment. In the future, maybe we try to see what is first order effect, first order moment, second order effect, second order moment. So as seen on our code, A is calculated by using effective creep, B is given by mechanical reinforcement ratio, C is using this first order in the moments, N is using axial load. For this example, let's take A 0.7 because effective creep is not given. B is 1.1 because mechanical reinforcement ratio is not given. And let calculate our C value because it depends on RM, which is calculated by using this first order moment from our bending moment diagram. End moments are given, first order end moment, which is double curvature by M01 is negative. In the case of single curvature, both are positive. So based on this calculation, our result RM is minus 0.75. So C is 2.2. N is calculated by using actual load, cross-sectional area of column, and concrete design strengths based on given characteristic strengths of our concrete, which is calculated by using this expression, which is provided on section 3 of this 1992 part 1. So FCD is calculating by using this expression. Alpha C is 0.85 as recommended by the code, and alpha C is partial safety factor for concrete is 1.5. we can see on this code on section 2.4.2.4. so by using this expression it calculates. So the result of FCD is 40.167. substitute the values. Our N is 0.228. so lambda limit is finally 71. If lambda calculated is greater than lambda limit, the column will be slender, otherwise it is short. Based on our result, lambda limit is greater than lambda calculated, which is 42.18 is less than 71, therefore the column is short. This is the end of our example. Okay, thank you for your watching. Subscribe, share, comment and like our video. Thank you for today.